Hello, I am Joseph Nolet, and I'll be discussing the transition metal iron today for a course I'm taking at Grand Canyon University. So just a quick overview of what we'll be diving into today will simply be where do we find iron, how do we isolate iron, its physical and chemical properties, its atomic structure, um, what's its bonding characteristics, as well as what compounds it typically makes. So, for example, like alloys in the case of iron, we'll see. Major uses, so other than the obvious ones, such as tools and the making of steel and things. Um, but we'll go a little more in depth about its uses more on a molecular level um, as well as we'll also include its impact on the environment and the human physiology, and what analytical methods can we use to um, discover whatever characteristic we're looking for in whatever we're studying. But beyond all of that, it's hopefully by the end of this presentation you feel that iron is a very important part of not only your personal life, but just life in general that goes around you. Like I sort of leaned over a little bit about the human health and physiology, um, as well as the ecology and environment that are also impacted by the iron cycle. Okay, so now that we've completed the uh, science introduction, let's just quickly go through the um, teaching part of it so that way you can get the mindset which I was uh, in when I created this presentation that in part I could potentially use for teaching the concepts behind iron and why it's so important to the world. So you can see here that there are 6 fundamental presumptions for this androgyny, and I tried to look through this whenever I made a slide so that way I can best accommodate the learners that my presentation was intended for. Um, so without going too deep, me being the lecturer, I would try to discuss all the concepts that we're trying to accomplish for the day, as well as for the subsequent classes, and solve any issues or difficulties that may arise along the way, so that way I can work my lesson plans accordingly. If, for example, going through this material and it end up being too difficult for them, then obviously I have to make the subsequent lessons a little more concise and a review of the material that was troublesome to them. So with that being included now, I think it's time to try our next part of the teaching plan. As just discussed, I'll be uh, utilizing those 6 pillars to help uh, add a backbone to my presentation so that way I can ensure that the information is presented in a logical format. But to be more specific, I would take it at a more direct introduction, seeing that the concept that we are covering here is a little more flat. It's not as theoretical or philosophical. Um, I feel that a direct instruction would best fit this because it's just regurgitation of knowledge. So that way we have a foundation to work from, and then we can discuss and dive deeper and create assignments accordingly that would make it worthwhile for the instructor, so they have, as well as the students, so that way the discussions they do have are um, thorough and not just simple 2 or 3 sentence answers. That there's something they had to actually use some thought behind, very thought provoking. Now that the education part is all resolved, and you got a feel for how I designed this presentation going forward, I guess the best step would be to define iron and fundamentally where iron belongs in the periodic table. As you can see here, it says transition metals is all in black, and Fe is right in the middle there, 26, which is for iron. So more specifically, it belongs to the middle section, which is also called the D block, which incorporates the fourth era and includes elements from groups 3 through 12. And just a quick note on why it's called the D block is that there's at least one biologically active d orbital electron for each of those metals. Now we're finally here with the star iron. What is it? Where does it come from? And how do we extract it or isolate it from the rest of the rock material? So first, as I said, Fe is the Latin shorthand for iron, um, and iron belongs thus to the group 8 of the periodic table, and after aluminum, iron is the fourth most common element overall. Iron is found in many different alloys. Firstly, you can see here on we have the magnetite, hematite, magnetic hematite, etc. But we also have kamacite, which is a low nickel meteorite iron, which could be found mostly in Greenland and the United States. The rest of these here, they have some significant contents of iron in conjunction with other metals, iron, or as we refer to it, iron ores. And they are extracted in the image we have on the side there, which is part of the smelting process where we have limestone and carbon, which they refer to as coke, which is used in the smelting process to remove the metal, in this case the iron that we want, from everything that we don't want. And that is used in what is called a blast furnace, where the molten metal is screened to remove any impurities that you obviously wouldn't want, seeing as you're going to be using iron to make different materials such as steel or cast iron, and with the more the impurities, the higher the probability of there be complications in the structure of the material. Now, it might be a little difficult to see, but right over here has the electron configuration, which, if you read along with me, it's argon. So the configuration for argon, then there are 6 electrons in the 3D and 2 electrons in the 4s orbitals, which means that there are 26 available electrons that can easily ionize due to the 3D and 4s electrons having comparatively close energies. There are 4 stable isotopes of iron that naturally occur, with the most prevalent being iron 56 and the least abundant being iron 58, while there's also iron 54 and 57 that have prevalence less than 6% combined, which is quite astounding in my research. Since iron is so widely used, iron also has trace quantities of carbon that can be absorbed from the choke during the smelting process, just previously discussed. There are also 3 main allotropes when it is pure, known as delta, gamma, and alpha iron, with the delta iron being solid at elevated temperatures, while alpha iron totally loses its ferromagnetism when heated above its Curie point. And gamma has a face-centered cubic structure and is paramagnetic, while delta and alpha iron has body-centered cubic structures. Now into bonding. Firstly, iron is very volatile and reacts vigorously with chlorine on mild heating, as well as with a variety of other non-metals. Mineral acids at low concentrations easily decompose metallic iron, and iron in its ferrous state, oxidized state, can be produced using non-oxidizing acids and without the presence of oxygen even. Iron has a number of documented oxidized states beyond the ferrous that I just mentioned, in that the other most prevalent is ferric, and they are most significant, and trends in the relative stabilities of oxidation states among elements of the first transition series um, as they continue to apply to iron as well. Now, iron has many different uses. You have the physical uses, such as machinery, tools, cars, train rails, and other frameworks for buildings, among thousands other daily necessities that have some form of iron, some alloy of iron included in it. But that then leads into the whole fact that iron by itself is actually quite brittle, so it needs to be mixed with some other um, metal in order to add some stability, um, both to its strength as well as its ability to um, be heated and cooled. And the structural uses of iron and its alloys heavily rely on their mechanical properties. There are several methods of assessing these qualities, such as the Brinell test, the Rockwell test, and the Vickers hardness tests. And that's partially why I included um, this image here on our slide, because that is how you would perform those tests. As you can see here, there's a hardness dial, there are test points, there's where you put the sample material, the table, and um, the handles to elevate the table so you can um, perform the test accordingly. And of course, there are also other methods you would be using. So in industrial setting, there's electrolytic refining is used to create pure iron. As the carbon concentration increases, the iron's hardness and tensile strength will subsequently increase, just like any other um, mix that iron happens to go with, in making its different alloys. And this takes us to iron being used as a catalyst. Since it is so cheap and harmless, why not investigate to see if it can be used? And for example, in the Fischer-Tropsch process, which converts carbon monoxide into hydrocarbons for fuels and lubricants, and the Haber-Bosch process, which generates ammonia, both frequently use iron catalysts. So since we saw those, we have scientists actively finding or investigating other ways to potentially use iron as a catalyst, because there uh, there are so many different ways. For example, iron 3 oxide and aluminum powder can be used to ignite to create thermite reactions, which can be used for welding large iron components such as railroads and purify ores, our circuit boards, water filtration, sewage treatment, textile dyeing, printing colors, animal feeds, etc. Um, Further use iron 3 chloride, while iron 3 chloride acts as iron 2 chloride acts as a catalyst to create magnetic iron oxides and iron complexes as well. As we just saw, iron can be used in a few situations as a catalyst, and that also reflects into the natural biogeochemical iron cycle as well. Because iron is a crucial component of aquatic ecosystems, it can serve as a nutrient limitation for um, plankton activity due to its diatoms and other phytoplanktic organisms. May experience slower development rates if their iron levels are too low. So in environments with lots of iron and little air, marine microbes can also oxidize iron. And we've also seen that sea ice in the Arctic plays a significant part in the storage and dispersal of iron in the ocean, removing iron from the water as it freezes in the winter and reintroducing it into the water as it thaws in the summer. With the supply of iron to primary producers can change due to variations in the iron cycle, as you can take a peek in that graphic there, from aqueous to particle forms as well. Now we've dealt so far with a lot of positives, so let me just quickly go through some of the negatives because unfortunately everything has some side effects. And of course, fortunately, the extraction of iron enriched ores, deforestation, peat production, agricultural drainage all have a negative impact on river ecosystems, or more specifically, um, the fish species and the abundance of them. So, like for example, some species died off, as well as the number of said species also has dwindled um, due to iron contamination. But that being said, antioxidants are a great natural way that the body helps in reducing the um, chances of iron toxicity by stopping molecular oxygen reactions, chelating the ferrous ions, maintaining the redox state of iron, and prevents iron from reducing molecular oxygen and trapping um, formed radicals, as well as vitamin E is also um, a non-enzymatic antioxidant that can stop damage caused by metals in vitro systems and animals loaded with iron, copper, and cadmium. With all that being considered, researchers from various fields are considering the role of trace metals in a variety of physiological and pathophysiological processes, with the most popular analytical methods being inductively coupled plasma mass spectroscopy, electrothermal atomic absorption spectroscopy, and total reflection X-ray fluorescence. Or for short, we have ICP-MS, ETAAS, and TXRF, respectively. Now, you're probably wondering, when will we hear something that actually applies to the real world? So here is the basis for one field of research study that was done by some scientists in China that fixed iron on both organic and inorganic materials to address the drawbacks, potential drawbacks at least, of using iron materials for wastewater treatment. Throughout the entire experiment, the iron 2 plus ions were found, and they were employed to eliminate heavy metals at the start of the experiment. And after multiple days, they found that heavy metals were actually effectively removed. And due to the low carbon source percentage in constructed wetlands, iron ions were utilized in the study to remove heavy metals via absorption and oxidation reduction reactions before acting as an electron donor. Additionally, the effluent's iron ion concentration was modest and did not further affect the ecosystem, as we, I guess, sort of already knew so far in what we've covered. To get to the point of it all, I already alluded to it, but they ended up finding that it was environmentally friendly to improve the um, pollutant removal capacity by adding iron-based materials. But further research should be performed to see how the microbial community changes when heavy metals and nitrogen interact with one another. In this presentation, which outlines the long history and current situation of iron, focuses on the properties and effects of iron on both the environment and human health. Um, we covered many different forms of iron, its alloys, the significant types of rocks that are used as iron ores because they combine with iron with other elements. We explored how the metal is taken out through the smelting process using limestone and carbon, which they commonly call coke. Um, Although iron is very volatile, it can be easily utilized and tested um, using many different methods, such as using hardness tests, such as Brunel, Rockwell, Vickers, or analytical tests, um, such as the inductively coupled plasma mass spectroscopy, um, electrothermal atomic absorption spectroscopy, total reflective X-ray fluorescence as well. And in our study, we end up seeing that iron is actually quite ecologically friendly. um, yeah, that's it's good for the environment, good for the human body. It's needed for um, different biological processes that we naturally have, and as well as the um, iron cycle that makes uh, our environment work as efficiently as it currently does, freezing, cooling, solidifying. But with all that being said, at the end of the day, iron is important for life on the planet in all aspects. We need it for our diets, tools, appliances, and, as mentioned, our ecosystem. So, next time you look at the periodic table, think twice before you judge an element before you truly get to know it. I've been your presenter for today, Joseph Nolet, and this has been for Grand Canyon University. So, hope this better gets you at least interested into pursuing research further into iron. Um, and if you have any questions, comments, or concerns, feel free to send them my way. You have my email, and on the note of the presentation um, being complete, thank you for this opportunity, and I look forward to improving my skills as a instructor, because I know that this is a long ways before I get there. So have a wonderful day, and I'll see you soon.